Announcement on the board that the first two lectures, not tomorrow morning, but Thursday morning, are postponed. The third speaker this afternoon is Koichi Shimada of Kyoto University. And the title of his lecture is A Classification of Real-Line Group Actions with Faithful Connes Takesaki Modulus on Hyperfinite Factors.
Thank you for the introduction, and I'd like to thank to the organizers for giving me an opportunity to talk at the Isaac Newton Institute. In this talk, first up, I'd like to explain the outline of the talk. And here, I'd like to talk about classification of R actions on hyperfinite factors. And the fundamental open problem is the following. That is, to classify R actions on hyperfinite factors up to cocycle conjugacy. And in this talk, I'd like to present the following partial answer. And that is let M be a hyperfinite factor which may be of type 3. And let alpha 1 and alpha 2 be two R actions on the hyperfinite factor such that both alpha 1 and alpha 2 are not approximated by inner automorphisms at any non-trivial point. And so we'd like to consider very outer actions, and this is assumption, and the conclusion is that then alpha 1 is cocycle conjugate to alpha 2 if and only if their invariants are same. Which I will explain later. Yeah, I'd like to talk about this kind of theorem, and as I will explain later, this is related to the uniqueness of the hyperfinite type 3-1 factor. Before strictly formulating the theorem, I'd like to explain the historical background. of classifying group actions. Why? Why some people are interested in classifying group actions? At least the first motivation to classify group actions was to classify hyperfinite factors. And this was considered by Connes. As you know, a hyperfinite factor is a factor which can be written as an increasing union of finite dimensional polynomial algebras. And in the early 1970s, it was a paramount issue to classify these hyperfinite factors. And Alan Connes solved most of the problems. And in his work, classifying Z actions played a crucial role. And what he did was to characterize the hyperfiniteness by a condition called the injectivity, and by using that characterization, he reduced the classification of hyperfinite factors to the classification of Z actions on hyperfinite 2-1 factors. And probably the highlight of his series of works is the characterization of injectivity as the hyperfiniteness. But here, we'd like to turn the spotlight on classifying Z actions. And part of Connes' theorem is the following. And he showed that all outer Z actions on the hyperfinite type 2-1 factor are mutually cocycle conjugate. Here, outer means that the action is not inner at any non-trivial point, and cocycle conjugacy means the following: two actions, alpha 1 and alpha 2, are said to be cocycle conjugate if there exists a map U from the group to the unitary element of the factor with UST is US alpha 1S UT and there exists an automorphism theta of M with a joint of UT times alpha 1T is theta times alpha 2T times theta inverse. Oh. Yeah. And you may feel it more natural to classify actions up to the usual conjugacy. That is, it may be more natural to classify actions without admitting the perturbation by this inner part. But in many cases, the usual conjugacy is so strong that it is almost impossible to classify all actions. And we would like to think of inner actions as trivial. And the usual conjugacy distinguishes inner actions from the trivial action. So I think classifying actions up to cocycle conjugacy makes sense. But anyway, I think this Connes theorem is quite amazing result because there are many outer actions. There are many apparently many outer actions on the hyperfinite type 2-1 factor. But Connes theorem states that when it comes to classifying up to cocycle conjugacy, all of them are same. And I think the following example illustrates the situation. Think of the hyperfinite type 2-1 factor as the infinite tensor product of n by n matrices. Then we can define an automorphism alpha by the shift of tensor component. Then it is well known that any power of alpha is outer for any non-zero I. So if we think of this as a z action, then this is an outer action. But these alphas are mutually non-conjugate. That is, if we choose different n, then we have different z actions, and they are really mutually non-conjugate. But Connes theorem states that they are mutually cocycle conjugate. So I think this Connes theorem is quite strong. And after Connes, some people are interested in classifying group actions and actions of discrete amenable groups on hyperfinite factors are completely classified by many people, such as Von Jones, Okunianu, Takesaki, Sadaran, and Kawahigashi, and Katayama, and recently Masuda gave a concise proof for the classification theorem, and his theorem is based on the sister algebra technique developed by Bradley, Elliott, and Evans and Kishimoto. But anyway, the discrete case is already finished. So one of the next problems is to classify R actions. But the R action case is much more difficult. And I think the following Kawahigashi's result exemplifies the difficulty of the problem. That is, Kawahigashi constructed an infinite family of R actions on the hyperfinite type 2-1 factor, such that they are not approximately inner. They are not inner at any non-trivial point, but they are not mutually cocycle conjugate. as I have said, when we consider Z action case, there is a unique outer action on the hyperfinite type 2 factor up to cocycle conjugacy. But when we consider R actions, there are many different R actions, outer R actions, which are not mutually cocycle conjugate. So the situation is more complicated, and I think just a mimicry of the discrete group case will not solve the problem. And indeed, there are some partial classification results obtained by Kawahigashi, Masuda or Tomatsu, but the complete classification is still an open problem. But I still think that classifying R actions is quite important. And indeed, classifying R actions is related to the uniqueness of the hyperfinite type 3-1 factor. That was shown by Haagerup. As you know,
I'm sorry.
sorry?
Whose name did you mention just now? I didn't catch the name just now. Oh, the connection with the.
They are connected. What?
Okay.
And
But after all, I thought that the uniqueness of the hyperfinite 3-1 is related to R actions on the 2 infinity.
yeah, and I don't know of who Takesaki, but probably it's not so difficult to see.
I thought that one was even shown to be unique up to conjugacy.
Yeah.
Well, at least if it scales the trace. So.
Yeah. And as you know, Haagerup showed the uniqueness of the hyperfinite type 3-1 factor. Type 3-1 factor. But this is equivalent to the following. Let R0, 0, 1 be the hyperfinite type 2 infinite factor. And let tau be the unbounded trace of this R01. As you know, any type 2 infinite factor has a unique unbounded trace up to scalar multiplication. So we fix one of them. Then all R actions on the hyperfinite type to infinite factor, which scale the trace at a certain speed, are mutually cocycle conjugate. Actually, this is also equivalent to the conjugacy. But here we want to consider cocycle conjugacy here. So, in some sense, the uniqueness of hyperfinite type Riemann factor corresponds to a classification of certain R actions on the hyperfinite type to infinite factor. So, yeah, classifying R actions on hyperfinite factors will extend this the uniqueness of hyperfinite type Riemann factor. So I think classifying R actions is quite important. And here, we would like to consider an analog of this Haagerup result. In the reference version of this Haagerup theorem, we consider R actions on type 2 infinite factor. And I think it's quite natural to consider its type 3 counterpart. But what is an appropriate setting? In the type 2 infinite case, we consider the following condition. Tau composed alpha is not identical with tau. Here alpha is an automorphism of the hyperfinite type 2 infinite factor. But this condition can be interpreted as a kind of an alterness. Because if alpha is inner, then this cannot happen because tau composed alpha of x is tau of ux u star. But because this tau is a trace, so this is tau of x. So inner automorphism does not satisfy this condition. And in fact, this condition, tau composed alpha is tau, characterizes the approximate innerness of an automorphism. So when we consider type 3 case, an appropriate setting is to classify R actions on type 3 hyperfinite factors which are not approximated by inner automorphism. Yeah. And so we would like to consider this kind of things. And in order to classify these actions, we need to consider an invariant. And so I would like to explain the invariant of the classification. That is called the Connes Takesaki module. That was constructed by Connes Takesaki in 1980s. And the Connes Takesaki module is a group homomorphism from the group of automorphisms of the factor to that of an abelian von Neumann algebra. And the actual construction is the following. Let M be a factor which may be of type 3. Then it has a natural R action on M, which is called the Connes Takesaki which is called the modular action. And here it's not so important what it really is, but the point is that this action is intrinsic to this factor, and the action which arising from the Tomita Takesaki theory. But anyway, this M has a natural R action, so we can take the cross product and we denote this by M tilde, and this M tilde has a natural R action theta defined by the following way. Theta t of x is x for any x in M. And theta t of lambda sigma s, and this comes from the real line, is exponential to minus 2 pi ist lambda s and if we restrict this to the center of M tilde, then we get an abelian von Neumann algebra with an R action. And we would like to consider a group homomorphism from the automorphism group of M to the automorphism group of this abelian von Neumann algebra. So take alpha in the automorphism group of M, and we would like to associate an automorphism of this abelian von Neumann algebra to this automorphism. And this is done by the following way. This alpha extends to M tilde, the cross product, by alpha tilde of x is alpha of x for x in M, and alpha tilde of lambda sigma p, sigma t, is something like some unitary element of M times lambda t sigma. And if we restrict this to the center of M tilde, then this is an automorphism of the center of M tilde, which commutes with the flow, the R action theta. And we call this the Connes Takesaki module of alpha. And this is an invariant. As an invariant, it's a little bit complicated, but sometimes this invariant is computable. Now we would like to state the main theorem of the talk. Let M be a hyperfinite factor and let alpha 1 and alpha 2 be two R actions on this M, which satisfies alpha 1t and alpha 2t are not approximated by inner automorphisms. And as I will explain later, this condition can be detected by Connes Takesaki module. That is, the Connes Takesaki module is not trivial at any non-trivial point. And this is the assumption. Then the conclusion is that alpha 1 is a cocycle conjugate to alpha 2 if and only if there exists an automorphism sigma of the center of M tilde which commutes with theta, an R action on M tilde, such that which conjugates alpha 2 to alpha 1. So, cocycle conjugacy can be detected as a conjugacy of R actions on an abelian von Neumann algebra. And
why do you just call this a partial solution?
Because that's not all actions, and we cannot classify this kind of.
Well, what are you going to?
We do not know whether we do not know the classification of these actions. No. Yeah.
Oh.
We do
Okay.
not. Yeah.
So it's only the
Yeah.
only the strictly really outer ones.
Yeah. Probably in order to, I think it's quite difficult.
What about the actual inner ones? I suppose they're actually inner.
Actually, inner.
Yeah. Then is that okay? Yeah.
And the inner case is always cocycle conjugate to the trivial one.
Yeah.
And yeah. And first, I will. I'd like to say that this theorem is not void. There are examples satisfying the assumption of the theorem, and the invariants can be computable. For example, let X be the two-dimensional torus, and then we can think of this as a measured space by the Lebesgue measure. And define an R action theta on L infinity by the following way. Theta t of f is a translation of f. And let theta 0 be an R action on M. No, on the hyperfinite type 2 infinite factor, which scales the trace. And then, if we take the cross product, by theta tensor theta 0, then it turns out that this is a hyperfinite type 3 type 3 factor. And we would like to consider R actions on this factor. And let beta be an R action on the L infinity defined by beta t of f is another translation. And let gamma be an R action on the hyperfinite type 2 infinite factor, which preserves the trace. Then this beta tensor gamma extends to M by alpha t of x is beta t tensor gamma t of x for x in L infinity tensor R01. And alpha t of lambda s is trivial. Then we can compute the invariant of this action. That is, the center of M tilde can be identified with L infinity, and the theta on z of M tilde corresponds to this theta, and the Connes Takesaki module of alpha t is beta t. So if we choose R1 and R2 in this beta, so that the ratio of R1 and R2 is irrational, then the Connes Takesaki module is faithful and which satisfies the assumption of our theorem. And if we choose different R1 and R2, they are mutually non-cocycle conjugate. But the action does not depend on the choice of gamma. If we choose different gammas, they are mutually cocycle conjugate. That's the example of the main theorem. And we give only one corollary of this theorem. Let alpha be an R action on a hyperfinite factor which satisfies our assumption. And let gamma be an R action on the hyperfinite type 2-1 factor. Then alpha tensor gamma is cocycle conjugate to alpha. This is because they have the same Connes Takesaki module. You may think this as a trivial, but I think without this kind of theorems, it would be quite difficult to show this kind of thing, I think. Finally, we would like to explain the ingredients of the proof. The main ingredient is a recent work of Masuda and Tomatsu. That is they considered the Lohorin property for R actions and gave a good criteria, good criterion for two actions, two Lohorin actions to be mutually cocycle conjugate. more precisely, two Loeffling actions are mutually cocycle conjugate if alpha 1 t times alpha 2 minus t is approximated by inner automorphisms at any point. I think their theorem is a profound result, this Loeffling property is a little bit technical and difficult property, and as far as I know, it is unclear what invariants can detect this property. So I think it's quite important what conditions imply this property. But anyway, thanks to their theorem, and the problem and our proof is reduced to the following two questions. The first one is whether our assumption implies the Loeffling property. And the second problem is, does Connes Takesaki module detect the approximate innerness? If we can solve these things, our main theorem follows. But this is already known. This is shown by Kawahigashi and Sutherland and Takesaki, I think in 92, and they showed that an automorphism is approximately inner if and only if its Connes Takesaki module is trivial. So the only problem is this one, and this is our technical achievement. And to show the first to show the to solve the first question, we need to use Okunian classification result. The two actions and Haagerup's result of uniqueness of type 3 one factor. By using these things, we can solve the first question, and which implies our main theorem. And so, in summary, we classified R actions on hyperfinite factors, which are very outer, and the invariant is an is an R action on an abelian von Neumann algebra. Yeah, I stop. Yeah.
Any questions or comments?
Yeah. Can you change a bit your group? Can you look at Z power D or something like that?
Sorry?
Can you look at other groups than than R? Like what kind of other group you could look for?
Another group.
Yeah.
Yeah. I think yeah. Actually, I haven't checked this yet, but at least this Masuda and Tomatsu result can be generalized for locally compact abelian groups, and maybe that's true for some kind of locally compact amenable groups, and probably this kind of theorem holds for more general groups, but I haven't checked.
Thank you very much.